Good afternoon, judges. We appreciate your time today and welcome you to our photovoltaic system proposal. Before we begin, the team would also like to thank the Solar District Cup organizers for this incredible opportunity. The Alamo Community Colleges team comprises 3 students from San Antonio College and Northeast Lakeview College. Alyssa Arcos majoring in civil engineering, managed conceptual design, and financial analysis. Rebecca West majoring in biomed engineering, managed the project proposal and development plan. And I, Candace Garza, majoring in cyber defense, managed the distribution impact summary and executive summary. Our team was assisted by our 2 advisors, Klaus Bartels, an engineering professor at San Antonio College, and Jason Pittman, the CEO to Big Sun Solar.
Cheyney University has deployed a new strategic plan committed to address the transition to a technologically advanced in education environments. They intend to utilize campus assets through partnerships that enhance research, learning opportunities, and academic excellence to every student. Cheyney is pursuing additional sources of revenue to ensure their financial stability, and the HBCU's mission is to serve as a model of social responsibility. And with the use of these partnerships, they'll be able to foster relationships with surrounding communities as the students develop solutions that impact their needs. Our solution directly aligns with Cheyney's mission as it facilitates opportunities for students, increases the marketability of Cheyney's resources, institutes a social purpose for students in addressing issues that their community, and the visibility of Cheyney's dedication to social justice and responsibility. The solution we've designed hosts 880 kilowatts of installed photovoltaics, 2,212 kilowatt hours of battery capacity, discharging at a maximum of 285 kilowatts, which will sustain the critical load of the life sciences building for over 8 hours. Through this competition, we were provided resources by NREL and HeatSpring that were instrumental in our research. When confronted by financial limitations, we explored organizations and available avenues with the interests of university expansion and STEM programs and climate action programs. In order to model our design, we were provided with software that is standard to the solar industry, such as Aurora Solar, Energy Toolbase, and the NREL Design Tools System Advisory Model. So we proposed 5 arrays across the campus with an average daily sunlight access of 4.2 hours. Our arrays are modeled to realistic production metrics. The light green pin that you see is our largest array. It's designed at 435 kilowatts, connecting to a battery system that's co-located with the critical load site that it must serve. The darker green pin is a flat rooftop array interconnecting to the Duckery building, and next to it is another flat roof system atop the library building. We've incorporated solar workspaces outside of these 2 buildings, which will promote collaboration against the backdrop of Pennsylvania greenery. The red pin is a flat roof system. It's atop the Ada George Dining Hall, and it incorporates covered patio seating for students and the surrounding communities to enjoy. Our final design is against a pitched portion of the new residence living dorm at the yellow pin. This location also incorporates solar benches for student use and for the socialization and gadget charging.
Our equipment selection includes Trina Solar 555 watt panels, a fully outfitted battery energy storage system by Cube Energy, hybrid inverters by Fimer, and all 3 racking types by Iron Ridge. The battery and panels share the same inverter, making our DC coupled system up to 3% more efficient than an AC battery system. These are the distribution considerations that we took into account when selecting said equipment. The voltage constraints demonstrated by our modules were largely defined by the provided heat map. On the heat map, the buildings where our arrays are located had high voltage levels. Our system's main source of thermal constraints originates from the battery. Our battery's efficiency is constrained by what its wires can sustain from overloading during energy generation. To combat these limitations, the battery leverages the power conditioning system, PCS, and HVAC system. The team decided to limit our system size such that all power produced would be used for campus loads or for charging the storage battery. The team was concerned about the probability of overcurrent with power being sent back onto the existing infrastructure. There is not enough hosting capacity on the current infrastructure to support large amounts of backfeed. We decided not to size up our battery because we determined that our battery needs PCS, reverse polarity protection, and a built-in inverter to combat the high probability of polarity switching, which could cause a system shutdown. Next. We decided to go with the fully outfitted energy storage system, which has 3-level protection to address interconnection limitations. In partnership with AP Systems, our inverter is outfitted with an external rapid shutdown system. The inverter is outfitted with 3 independent MPPTs that consider interconnection constraints and limits power sent out to the grid. The MPPTs monitor and adjust to align with the export limitations.
Our system follows a peak shaving algorithm, which is able to deploy the battery at specific times, avoiding spikes in consumption and demand charges. The Cheyney's distribution needs are constrained by the timing of the peak loads, but our design targets all of the available daytime grid loads. Next. Competing with the low industrial energy costs, while simultaneously meeting the needs and goals of the school requires outside funding. We decided that a system that meets the campus needs should be modeled because we're confident that in Cheyney's abilities to access said funding by employing either a green revolving fund program or providing community training and gaining access to the manufacturing PA initiative, which may actually already be available through the new cybersecurity training that Cheyney's just begun to offer.
Now, Cheyney is in a unique situation since it straddles 2 counties. Delaware County does not have specific codes for PV systems. Chester County, on the other hand, does specify regulations for PV systems, so we elected to apply their codes and ordinances campus-wide. These influence placement and design of each individual system. PICO only really specifies that installation be performed by a qualified contractor, which we would never dream of advocating against even without said rule. On the state level, Philadelphia does not have specifics for photovoltaic systems. On the federal level, however, we were able to consult the national fire codes to determine requirements. These include the voltage requirements, rapid shutdowns, grounding, and of course, the capability to isolate the system. Another unique situation for Cheyney University is the impending partnership with Sonali. Manufacturing their own equipment paired with visible arrays that are already set up and harvesting power will make Cheyney a field trip destination. They will be capable of providing learning opportunities to people of all ages throughout their community and beyond. The manufacturing plant also sets Cheyney up to be able to provide internships and jobs to students or other community members. This aspect can also help cut the cost of their own PV systems. The development timeline starts with the permitting process. This could take up to 15 weeks between submitting, processing, and deliberations. We are allotting approximately 16 weeks for procurement, especially since manufacturing and distribution chains have been slowed and sometimes altogether halted due to COVID. Construction will also take approximately 16 weeks. This timeline was put together with the assumption that Cheyney would be purchasing the equipment from an external source since the manufacturing plant does not yet exist. If they delay until they are able to manufacture their own panels, the timeline will change drastically.
Our system aligns with the social justice values of Cheyney in conserving resources for future generations by avoiding all of these large negative impacts on the climate.
When all is said and done, our system will launch Cheyney University into their intended future. This plan provides the group of systems that will play directly into their goal of manufacturing their own solar equipment. Thank you.